So couple of things, just again, reminders. If you are absent, first place you should always check is Google Classroom. As far as handouts, things like that, I typically will put a PDF version of that in Google Classroom if you're out. Other thing, going through, I reopened Chapter 3 until Friday. Some of you are not keeping up with the online active stuff. And I'm telling you again, that's going to be a lifesaver, especially after you take the DE test. It replaces one of those scores. So you want to keep that average as high as you can. If you're getting 40s and 50s on the homeworks, that's not going to help you. All right. So you want to try to maintain that high average, at least a 90 or above on those. It's okay to miss a few problems, but not doing half of it is not going to work. And even that is going to be something that even if you were to withdraw from the DE, those homeworks are still going to count as grades for me. So just keep that in mind. The other thing, so as we're moving forward, again, we're covering Chapter 4 right now. That will actually put us at the point where we're finished the material before the first test. I am going to try to give you some sort of practice test for it. That's not the exact same as the DE test, but it's going to give you the same information. We'll be testing the same material. So just trying to set you up for success on that, and you can use that to help you prepare over the break, because we're going to be taking that DE test right after we get back. Yesterday, we started looking at certain scientists that have contributed to atomic models, specifically Dalton, Rutherford, Thomson, and Bohr. Today, we're going to move a little bit forward looking at the pieces of the atoms, the subatomic particles, proton, neutron, electron. The things that we need to know about that, we need to know their location, their charge, and their relative mass compared to each other. We will also start looking at elements as far as a neutral atom in terms of an ion and in terms of an isotope, and try to see how each of those are different and how those things represent differently. And going into that. So starting off today, if I had a baseball and I represented that as a singular proton, the size difference and mass difference would be relative to carrying a baseball to a grain of rice. All right. So comparatively speaking, the electron is pretty much insignificant in mass compared to the proton and the neutron. So when we talk about masses of atoms, if you look on the periodic table, if you look on your periodic table reference packet, the number that's typically written down at the bottom of an atom's box. So if we're looking at carbon, for example, it's 12.01. All right, it's 12.011, sorry. So if we're looking at this representation of the mass is telling us a couple of things. So this is mass. This is atomic number. All right. Atomic number is essentially protons. Mass is the protons plus neutron. All right. So that's a total number between the protons and the neutrons. Now, the reason why we have decimals after those is because that's an average of all the different versions of that compound. So when I'm looking at carbon, based on a mass of 12, I can say that this carbon has 6 protons and it has 6 neutrons. As far as the number of electrons, I have to look at the state of the atom. Is it an ion or is it a neutral atom? If it's neutral, it's going to have the same number of electrons as it does protons. If it's not neutral, it's going to have a varying amount, and we'll have to do that based off the charge. So getting into this, when we look at our periodic table that we have in the reference packet, remember, the one that we have and the one that Southeastern Lessons used on the test does not have the names on it. I gave you a list of elements that you need to know the names and the symbols to. All right. It's pretty much relative is just about the first 52, but there are some that are scattered throughout, and we don't need to know all of them. You're going to find we don't pay a whole lot of attention to this center section right here, transition metals, as we're going through this, because they don't follow all the rules for charge and things like that the way everything else does. So it's kind of hard to describe those in specific ways. So everything else on here we have to just kind of look at, and we're going to compare things to each other on this chart, and all of that. What I will say, just looking at this, everything on this periodic table is based off of carbon. We established the mass for carbon and compared everything else back to carbon. They've tried it different ways. At one time, they were trying to base it off of oxygen, and that was throwing a lot of numbers off for 2 reasons. One, oxygen is a diatomic molecule, and then the other reason, since oxygen is primarily as a gas form, is very hard to compare it to, whereas carbon has a relatively stable singular isotope. All right, so let's get into it. All right, we started talking about this yesterday, but there are some common things that we need to know. When we're dealing with atoms, we're primarily 2 particles identify charge: proton and electron. Proton is always positive, electron is always negative. So some things to remember is electrical charge is fundamental of protons and electrons, and that opposite charges attract. So a positive and a negative electrical charge will attract towards each other. Electrostatic attraction. If you've ever forgotten to put your dryer sheet in your dryer when you're drying clothes, especially things like sweaters or sweatshirts, you've probably experienced electrostatic attraction where a sock is stuck to your sweatshirt or something like that. All right, or if you've ever done the little thing where you have the hole punch stuff, and you take a balloon and you go over it, and they'll attract to the balloon. So if we ever have like charges, positive or negative, they repel. Let me make sure I'm. Now, we are going to talk about the mass of these things again. Remember, a proton is much larger and much more massive than an electron, but as far as charge is concerned, a singular proton has a positive charge of 1, magnitude 1. Electron has a negative charge of 1, magnitude 1. They are equal and opposite in charge. They cancel each other out. So even though the size difference is large, the charge is equivalent. All right, they are equal and opposite, so they cancel each other out. So one proton and one electron makes a net zero charge, or a zero charge. So again, just kind of going through the diagrams on the side. So the red represents a proton, the yellow represents an electron. So if I have a proton-electron interaction, they are going to pull towards each other and attach to each other. If I have a proton-proton or an electron-electron, they're going to push away from each other. And then again, the charges are equal and opposite. They will cancel each other out. So it gives us an overall, if I have one proton, one electron, gives us an overall zero charge. So going back to my carbon atom that I was talking about, I said that we have 6 protons, we have 6 neutrons based off of our atomic mass. And then if I wanted to know how many electrons there are, if I said that if I'm just pulling it off the periodic table and I don't say anything else about it, we assume it's neutral. So that would mean this has 6 electrons. If we went back to the Bohr model that we talked about yesterday, if I were to draw that, and I'm going to draw a partial Bohr model, so proton 6, neutron 6, and then carbon is in the second row. So in my first energy level, it has 2. In my second energy level, it has 4 electrons. All right, so, and that's just 2 pairs of electrons on it. Questions about that? All right. So just kind of, now we're going to start individually talking about protons, neutrons, and electrons. So the first thing is, as far as mass is concerned, a proton and a neutron are very similar in mass. They're approximately the same size. We assign a unit called an atomic mass unit to it. So each one represents pretty much 1 AMU. So one proton is 1 AMU, one neutron is 1 AMU. So when we look at those, that's why I can say the mass is the protons plus the neutrons. All right. Electrons comparatively have almost a negligible mass, meaning it's kind of meaningless. And when we start talking about this, the largest element that are the atom or element that we have that has the most electrons in it would be this one with 118. Even though we have 118 electrons on this, it's still negligible compared to one proton, because each electron is 1/2000th of the size of the mass of a proton. So it would take 2,000 electrons before I even get a significant mass of them, comparatively. All right. So we will look at this data table real quick. So we have 3 subatomic particles that we're going to worry about. There are more subatomic particles because we can break a proton or neutron down into smaller parts. We can break those down into quarks. We can break them down into positrons. We can break them down into beta particles. All right. But in this class, when you see me writing the notes, I will always represent a proton as a lowercase p with a little positive symbol next to it. I will always represent a neutron with a lowercase n and a little 0 sign raised to the 0 power. And I'll always represent an electron with a lowercase e and a negative sign. Now, again, notice the mass of the proton and the neutron there. This unit called an AMU is, again, like every other measurement that we use, AMUs are made up, and it just stands for atomic mass units. Sometimes some textbooks will leave out the M and just call it an AU, atomic unit, but it means the same thing. But notice that there's very little difference between these. You don't start seeing the difference until the thousandths place in the decimal. So the difference in mass is negligible for between a proton and a neutron. However, pay attention to the charge. Proton is a +1. A neutron is 0 charge. It has no charge. So to remind you of a Mr. Gilliatt joke, a proton and a neutron walk into a bar. Proton asks for a drink. And then the neutron asks for a drink and he says, how much? And the bartender says, for you, no charge. Sorry. Very flat today. All right. Anyway. No, it's not. But it's, all right. So. All right. Now, I want to say the electron's mass is essentially 1/2000th of the mass of a proton or a neutron. I think the number comes up to be like 0.001986, and we just average it to the 2000s place. But I don't need us to know the exact number. I just need us to know that it's very, very, very small in comparison for mass. But again, even though the size difference and the mass difference is that much, when we look at charge, they're equal and opposite, 1 and 1. All right. And remember, in this class, when we talk about positive and negative, it's more about direction than it is a true negative like you would look at in a math class. All right. All right. So I want you to draw a table real quick in your notes. 6 columns, 5 rows. It's going to look something like this. Across the top, we'll have the element name, atomic number, mass number, number of protons, number of neutrons, and number of electrons. And you're going to probably want to have out your periodic table reference packet so that you can use your periodic table for this. All right. So one of the skills that we're going to need to have is to be able to use the periodic table to determine the number of protons, neutrons, and electrons in an atom. And this is going to represent neutral atoms. So when I say neutral, what does that mean in terms of charge? No charge, 0, right? So we are looking, so in terms of protons and neutrons, what does that mean the number is going to be on those? Not 0. They're always going to be equal amounts, right? So if I have 1 proton, I'll have to have 1 electron. Sorry, not neutrons. 1 proton, 1 electron. If I have 20 protons, that means I have to have 20 electrons. All right. So using your periodic table, What is the atomic number of the element with the symbol Ca? It's 20. What does that number tell us? All right. So remember, atomic number equals protons. So atomic numbers is always the same as the number of protons. So in this case, if I have 20 atomic number of 20, that means I have 20 protons. Now, when I look at it in terms of atomic mass, or the atomic mass number, I don't want the number that they're giving us on the periodic table. I want us to round that number to the nearest whole number. So if I look at calcium on here is 40.078. So for my mass number, I'm just going to write 40 in this case. Now that I have the mass number, what else does that tell me? That the neutrons are also 20. All right. Now, if this is a neutral atom, what does that mean the electrons have to be as well? 20. So since this number is 20, if it's neutral, that makes that 20. So in terms of charge, and you don't have to write this column, the charge should be 0 on all of these, all right, if the number of protons and electrons are equal. All right, so go ahead, use your periodic table to answer the rest of these, see what you come up with. For the most part, a lot of times you're going to see, until you start getting into the heavier elements, protons and neutrons tend to be equal. Once you start getting past row 4, then you start seeing a big disparity between the protons and the neutrons. So go ahead, identify for the rest of these. And while you're doing it, I'll be doing it up here as well. Thank you. All right. So, looking at magnesium, how many neutrons would I have? 12. And I'm also going to have 12 electrons. So, looking at sodium, sodium's got 11 protons. For it to be a 0 charge, it has to have 11 electrons. How many? The mass number for sodium is 22.99. So we can round that to 23. How many neutrons does that give us? 12. All right. So notice that the neutrons and the protons are not always equal, but a lot of times they will be. And then helium. Helium's, if it has 2 protons, that means it has to have 2 electrons in a neutral case. And then it's got a mass of 4, so it has 2 neutrons. All right, questions about this? Yes? Yes. So neutrons is always going to be equal to the atomic mass I'm just going to put rounded atomic mass minus the protons. our atomic number. All right. So neutrons is equal to the atomic mass minus the atomic number. All right. Now, so this is for, again, reminding you that if I'm just pulling it off the periodic table and I don't say anything else about the atom, I just give you the symbol, we assume it's neutral. All right. The next type that we're going to deal with is an ion. All right. So we have two types of ions. An ion is a charged atom. We have a cation, which is positive, and we have an anion, which is negative. All right. That also relates to battery stuff with like cathode and anode and all of that. All right. Now, using our periodic table, and you can write these numbers on yours just to kind of help you remember, there are certain columns and certain areas on the periodic table that just by the location of the element, we know the charge. So, including hydrogen in this one, everything in group 1A tends to make a +1 charge. A lot of times you're just going to see it as a positive sign without a number, but because we have one positive sign, we assume 1. All right. Everything in group 2A is going to be a +2 charge. We can't identify the charge on these without other information, because these charges can vary based on interactions with other things. So I can't put a charge on any of these in the transition group. But coming over here, a lot of your periodic tables and the one that I gave you, you should see kind of a bolded stair-step line here. Like that. Everything above this line is considered to be either a metalloid or a non-metal. So we don't really assign charges to the metalloids going across. But the metals that are below this, we can assign charges. And all of these are going to end up being a +3 or a 3+. So group 3A tends to have a +3 charge. I'm going to skip this one. Things above the line here, so like nitrogen, phosphorus, and arsenic, if they're going to make a charge, tend to be -3, and then this column will tend to be -2, -1, and then that column is always 0. So the location on the periodic table can help us determine the charge. It doesn't always, especially kind of in this region right here, it's kind of hard to know charge sometimes. But if below this line is probably going to be a positive, if it's above the line, it's going to be a negative. It's kind of where you treat it. Now, group 4A, the whole goal is to kind of get to 8 electrons total in the outer shell. So if we're looking at the numbers, what's happening here, I go +1, +2, +3, -3, -2, -1, 0. So right here, we're kind of in the middle. So these can end up being like a + or -4, but there's some variation in those numbers. All right. But it can be both. It can be either plus or minus. So like carbon and silicone, If they're going to make an ion, they're going to make a negative ion that's typically a -4, and the ones below it will tend to make a positive ion that's a +4. But it's at that halfway point that we're dealing with here. All right. So now, in order to create an ion, can I remove, or let's back up. What are the only two particles that are charged? Proton and electron, right? Proton is positive charge, electron is negative charge. All right. Can I remove a proton from an atom and it still be what it is? No. So what is the only thing that I can remove or add to change the charge of an atom? Electrons. So in order to make a positive atom, to make a positive ion, do I have to remove electrons or add them? Remove. So for this to be a +1, I've had to remove 1 electron. For this to be a +2, I've had to remove 2 electrons. Over here, how do I get to a -3 charge? Add 3 electrons. So I'm going to have, so looking at nitrogen, a nitrogen ion is going to have 3 more electrons than it has protons. So nitrogen has 7 protons. That means it'll have 10 electrons in the ion of it. So I'm going to continue that conversation on this slide. All right. So if we're looking at lithium, if I want to make lithium into an ion, so in order for lithium to become a +1 ion, it has to lose 1 electron. So it goes from neutral lithium to lithium and 1 electron that's going off into space somewhere. All right. So the charge of an ion depends on how many electrons that are gained or lost. The charge of the ion will depend on how many electrons are gained or lost. So again, if I gain electrons, that's going to produce a negative charge. If I lose electrons, that's going to produce a positive charge. All right, so looking at another example, if I want to create an ion from fluorine, fluorine wants to gain an electron to get to 8. So fluorine is going to form a -1. So fluorine is going to take on an electron and become a -1 charge. All right. So earlier, I told you that group 6A, the one that oxygen is in. So when oxygen forms an ion, oxygen becomes a -2 charge. So in order to do that, do I have to gain or lose? Have to gain. How many do I have to gain? 2. So in order for oxygen to become an ion, I have to gain 2 electrons for that to happen. All right. Earlier I said aluminum makes a +3 charge. How do I accomplish that? I have to lose 3 electrons. So So when I'm writing this, I'm just showing if the electrons are being lost, I show it over on the product side where the electrons are going away. If I'm gaining the electrons, I show it on the reactant side. Then I'm adding those two electrons to it, and it becomes there. All right.
Wait, so the oxygen when it's stated that's gaining or losing?
So on the reacting side, so it's gaining. That is a gain. I'm gaining electrons, so I become more negative. Here I'm losing electrons, so I become more positive. All right, so you're going to create a table again, just like the one before. So it's going to look just like the one before, except for this time we're going to deal with ions. So all right, does anybody need more time on this slide? All right. Now, looking at this one real quick, what do you notice different about the way that I wrote the symbols on this one compared to the previous table? So when we look here, like zinc has a +2 charge on it. Iron has a +3. So I'm showing a charge this time. Before I was just showing the symbol without any charge. So again, remember proton is a plus, neutron is a 0, electron is a negative. So we'll do fluorine together real quick, and then I'll let you take a minute and do it on your own. So fluorine has an atomic number of 9. So what does that atomic number tell us? It tells us protons, right? That never changes. Atomic number always equals the protons. Now, the other thing that I see is that fluorine has a negative charge right here, just a singular negative charge. So what does that tell me about the number of electrons? It's going to be one more electron than proton, right? So that means that I have 10 electrons because I gained an electron. Now, in order to get the neutrons, I need to know this number. So fluorine's mass is 18.9984. So I can round that to 19. So 19 minus 9 gives us 10 as well. All right. It's just coincidental that the number of neutrons and the number of electrons equaled each other. Mass minus number. Yeah. Mass minus protons gives us neutrons. All right, so go ahead and see what you get for the rest of these. Yeah, but you're not going to add any protons to it. You're just going to remove electrons, yes. So the only number that's going to change is this number. All right. It's the number at the top on your periodic table. Look at this page. That's electronegativity. We're not there yet. Huh? Yeah. So if it just has a symbol, it's just a charge of 1. All right. So when we look at an atom, there's only 2 numbers that I can manipulate. Neutrons can vary, and electrons can vary. Protons have to be what they are. So whatever your atomic number is, it always has to equal this number, no matter if it's an ion, no matter if it's neutral, no matter if it's an isotope. The thing that can change is the number of neutrons. We can add and remove neutrons, and we can add and remove electrons, and it still be that element. All right. So on this one, because it's an ion, this number is going to change compared to the protons. All right. So zinc is a +2. How does that affect my number of electrons related to my number of protons? It's going to be 2 less. So how many electrons do I have? 28. Because +30 plus -28 equals a +2, right? Iron is a +3 overall charge. So how is that going to affect my number of, it's going to have 3 fewer electrons, so 26 minus 3 is 23. All right. Iodine has a -1 charge. So I'm going to add 1 electron. So that's going to be 54. Lithium, guys, lithium has a +1 charge. So that means I have 2 electrons. So notice, whenever the number is positive, I have more protons than I have electrons. Whenever the number is negative, I have more electrons than protons. All right. Now, going through here, 65 minus 30 gives me 35. 56 minus 26 is 30. 19 minus 9, we already did 10. 127 minus 53. And I don't feel like doing that one in my head. Thank you. All right, and then 7 minus 3 is 4. All right, so before we move off of ions, does everybody know the difference between a neutral atom and an ion? Okay. Neutral atom has no charge. Ions have a charge. All right. Does everybody recognize the way that I'm going to show an ion versus a neutral atom? So that represents an ion. If it doesn't have a charge on it, then it's neutral. So it'd just be Zn as an atom. All right. That brings us so the last category that we're going to talk about today is an isotope. If you did, it's probably not the same thing. All right. For us, an isotope. So a couple of things that we need to remember about to identify an isotope. An isotope, remember, every atom of gold, what is every atom of gold always going to have in common? It's going to have 79 protons, all right? Protons cannot change. We can change the number of neutrons, though. So all atoms of a given element will have the same number of protons. Gold always has to have 79 protons. But gold doesn't always have to have the same number of neutrons. And varying the number of neutrons can make the difference between that atom of gold being radioactive or not. All right. But if for the first couple of rows, we pretty much see an almost one-to-one ratio between protons and neutrons, and that makes a stable element. If we start getting outside of that one-to-one ratio in these first couple of rows, then it becomes unstable or radioactive. As we get to the heavier elements, it usually ends up being about 1 to 1.5 for stability. And then down here, we haven't found a stability point yet. So the bigger the element, typically the more neutrons you need compared to protons to make it stable. And so when we're looking at this, there are radioactive versions of gold. You know, chemistry, where chemistry has its roots in is alchemy. Alchemy was basically, they were trying to take non-precious elements and make precious things like gold. So they were trying to create gold from things that are cheap. All right. And that's kind of the root of it. And there's a lot of mythos around it and all of that. But we can create gold from lead now. We can transmute it. We can bombard it with protons and neutrons and turn it into something else. But when we do that, the gold that we create is not going to be gold that you can go spend, because it's radioactive and it's going to fall apart, and it's going to go back into another element again. All right, because it's going to decay. And so that's the problem with radioactive stuff. I mean, I guess you could pass it off to somebody and either make them sick, or they'll sit in the vault somewhere and then it'll turn back into something else later. But odds are they're going to test that. All right, so atoms of a given element have the same number of protons. They don't have to necessarily always have the same amount of neutrons. So what we were doing before, where we take the mass number off of here and subtract the atomic number, that works for just a regular neutral atom, and it works for an ion. For an isotope, I have to tell you what the mass of that isotope is. So the definition of isotope is right here. An isotope is an atom with the same number of protons, but the number of neutrons are different. We have varied the number of neutrons. So all atoms have their own unique percent of natural abundance. So for carbon, for example, has 2 to 3 different versions of carbon. We can have what we call carbon 12, which is the standard version of carbon, but we can also have carbon 10, and we can have carbon 14. Does anybody know the significance of carbon 14 or what we use it for? All right, so anything that's considered to be organic on the planet has carbon in it, including us. Carbon 14 is a radioactive isotope of carbon that allows us to measure, if we can look at the percentage of carbon 14 in a fossil or in something that was once organic, and we can tell how old it was approximately, carbon dating. Carbon 14 has a half-life of like 1,760 years. So if something is 20,000 years old, we can get an approximation within about 2,000 years of when it was alive. So just by looking at the percentage of carbon 14. So with these 3 versions of carbon here, remember that, and I'm going to explain what these symbols mean in a minute. But remember that all of these carbons have 6 protons in them, right? So what's changing about them is the number of neutrons. This one has 6. This one has 8. No, 4. Sorry. And this one has 14, 12, 8. That's where I was trying to get the 8. Yeah, thank you. My brain just froze. All right. So carbon 10 has fewer neutrons than carbon 12. Carbon 14 has more neutrons than carbon 12. And that's the only difference there. All right. So let's look at, all right. So neon has 3 different versions as well. And I'm going to identify what all these parts mean. So one of the ways that we represent an isotope is with something called isotope notation. We can also show an isotope as an ion as well by adding a charge on the other side. So there's a lot of information that we can put into a symbol when we write it. So when I write isotope notation, the number that I'm showing right here at the top is my mass. I am telling you what the mass of this is. All right. The number at the lower left-hand corner is the atomic number. And then obviously the chemical symbol. That's something that hadn't changed. Now, I can write isotope notation like this and tell you that this is neon 20, this is neon 21, this is neon 22. Or you might see it written instead of like this, it might be written like NEON hyphen 20. You can see it written both ways. You can see it written in isotope notation, or you can see it written in as an isotope name. No matter what, this represents the atomic mass, that represents the atomic mass. This represents atomic mass, that represents atomic mass. Atomic mass, atomic mass. All right. So no matter which way it's written, that's going to show you the atomic mass. Do I always need to show the atomic number? Why not? If I tell you it's neon, do I know the atomic number for it? Yeah, because I can look it up right there. The atomic number does not change, but the mass can. The mass can change. Also notice that on these, which one of these do you think is the most abundant isotope in nature based off of what you see on the periodic table? Which one's going to have the highest percentage that we're going to find in nature the most? Looking at neon, looking at the mass of neon is on average atomic mass on the periodic table is 20.1789. So it's not 21, it's closer to 20. So I'd say this one probably has the highest percentage of abundance because if I had a higher percentage abundance of this one, it would be a higher mass number on there because that's an average of all of them. All right. So when we do this, so I'm going to pull this over here real quick. Now, the mass number can change, just like the charge can change. All right. So if I'm looking at neon 22, how many protons does neon 22 have? All right. How many electrons does neon 22 have? 10. Do I have anything to indicate charge on this symbol? So it's going to be, these two are going to be equal now. How do I find out the number of neutrons? The mass minus the protons. So 22 minus 10 gives us 12. All right. Now, this is probably a not a real thing. Huh? Yeah, I have a class next door that sometimes uses my back door. They'll come in and out sometimes. No, Coach Smothers and takes his student out that way sometimes. All right, so let's look at this one this time. This is probably not a real thing because I don't think you can make a. I don't. You typically won't see a noble gas like neon being an ion, but let's just pretend for a minute that I have neon 21 with a +2 charge. So this one, if I'm looking at it in terms of protons, neutrons, and electrons, what things have changed about this one? All right, so protons is still 10.
Electrons is 8. 11.
All right, so notice that both of these have the ability to change, but the protons never change. That's kind of my thing that I want you to get out of this. All right. So I already kind of showed y'all this, but again, we can also, instead of calling it isotope notation, we can also write it as, we can notate an isotope like this. Just remember that the number associated represents a mass. That's where I'm going to stop today. Hey guys, I need y'all to pick those heads up, please. Thank you. All right. So, let me, this is where we're going to end the notes today. So we're going to do